Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Isaac Newton's A Treatise of the System of the World, emerging in 1700, provides an accessible distillation of the profoundly influential ideas presented in his Principia Mathematica, where the Principia offered a rigorous, geometrically dense, and often challenging exposition of his laws of motion and universal gravitation. The treatise presented these concepts in a more readily digestible format, aiming for a wider audience. This accessible, however, belies the depth and significance of the work, serving as a bridge in disseminating new revolutionary work. The genesis of the treatise lies in Newton's desire to elucidate the cosmological implications of his physics. While the Principia meticulously established the mathematical framework, the treatise sought to showcase its explanatory power, applying these laws to the celestial realm and demonstrating how they could account for the observed motions of planets, comets, and other celestial bodies. It addressed a world still grappling with the transition from Aristotelian physics to a mechanistic understanding of the cosmos. Prior to Newton, explanations of celestial phenomena often relied on complex systems of epicycles and deference, inherited from Ptolemy and refined over centuries. These models, while capable of predicting planetary positions with reasonable accuracy, lacked a unifying physical principle. Newton offered precisely that: a single, universal force governing all matter, from earthly objects to the most distant. Newton's Principia, published in 1687, provided the foundation for the treatise. The Principia established three fundamental laws of motion. First, an object remains at rest or in uniform motion unless acted upon by a force. Second, force equals mass times acceleration. Third, for every action, there is an equal and opposite reaction, coupled with his law of universal gravitation, which states that the gravitational force between two objects is proportional to the product of their masses, and inversely proportional to the square of the distance between them. These laws provided a comprehensive framework for understanding the physical world. Stated explicitly, the gravitational force, F, equals capital G, the gravitational constant, times m1, the mass of the first object, times m2, the mass of the second object, divided by r squared, the square of the distance between their centres. The Principia used these laws to explain Kepler's laws of planetary motion, demonstrating that these laws were consequences of a more fundamental physical principle. The treatise strategically omitted much of the complex geometric proofs and derivations characteristic of the Principia. Instead, it focused on presenting the results in a clear and persuasive manner, emphasizing the empirical evidence supporting his theories. For instance, the treatise vividly describes how the gravitational attraction between the Earth and the Moon accounts for the tides, a phenomenon previously attributed to mysterious influences. It also explains the precession of the equinoxes, a slow wobble in the Earth's axis of rotation, as a consequence of the gravitational forces exerted by the Sun and Moon on the Earth's equatorial bulge. These explanations, grounded in a single, elegant physical principle, offered a compelling alternative to the more convoluted explanations prevalent at the time. The treatise presents a vivid, if somewhat idealized, picture of a clockwork universe governed by immutable. One immediate application of Newton's work was in the refinement of astronomical predictions. By applying his laws of gravitation, astronomers could calculate planetary positions with greater accuracy. Halley's prediction of the return of the comet that now bears his name is a testament to the power of Newtonian physics. Halley, using Newton's laws, calculated the comet's orbit and predicted its reappearance in 1758, a prediction that was fulfilled, solidifying Newton's theory and marking a turning point in the acceptance of his ideas. This success demonstrated the practical utility of Newton's work, not merely as an abstract theoretical framework, but as a tool for making verifiable predictions about the natural. The treatise, and Newtonian physics in general, profoundly influenced subsequent scientific developments. The development of celestial mechanics, particularly by figures such as Laplace and Lagrange, built directly upon Newton's foundations. Laplace's mécanique céleste, for instance, extended Newton's work to account for the mutual gravitational interactions of all the planets in the solar system, providing an even more accurate and complete description of their motions. Lagrange's work, on the other hand, introduced new mathematical tools and techniques for analyzing dynamical systems, further expanding the scope and power of Newtonian mechanics. Furthermore, the success of Newtonian physics inspired scientists to search for similar unifying principles in other areas of physics, leading to the development of electromagnetism and thermodynamics. The reductionist approach, Viewing the universe as governed by fundamental laws became a guiding principle in scientific inquiry. Despite its immense success, Newtonian physics faced challenges and revisions. One significant challenge stemmed from the discovery of anomalies in the orbit of Mercury. The observed precession of Mercury's perihelion, the point in its orbit closest to the Sun, could not be fully explained by Newtonian gravity, even when accounting for the gravitational influence of all the other planets. This anomaly remained a puzzle until the advent of Einstein's theory of general relativity, which provided a more accurate description of gravity, especially in strong gravitational fields. Einstein's theory explained Mercury's anomalous precession and predicted other phenomena, such as the bending of light by gravity, which was subsequently confirmed by observation. Thus, while Newtonian physics remains an excellent approximation for many phenomena, it is an approximation. There exist circumstances where it breaks down, necessitating a more complete theory. The reception of Newton's work was mixed initially. While many scientists and mathematicians recognized the power and elegance of his theories, others were hesitant to abandon established Aristotelian views. The emphasis on mathematical reasoning, rather than qualitative descriptions, also posed a challenge to some. Moreover, the concept of action at a distance, the idea that gravity could act between objects separated by empty space, was initially viewed with suspicion. Critics argue that it seemed to imply a kind of occult force, reminiscent of the explanations Newton sought to supersede. Over time, however, the overwhelming success of Newtonian physics in explaining a wide range of phenomena led to its widespread acceptance. The treatise, with its accessible presentation, played a crucial role in this process. It facilitated the dissemination of Newton's ideas to a broader audience, helping to overcome initial resistance and paving the way for the triumph of Newtonian science. Newton's direct influences included the work of Johannes Kepler, Galileo Galilei, and Christian Huygens. Kepler's laws of planetary motion provided the empirical basis for Newton's theory of gravitation. Galileo's experiments on motion and falling bodies helped to establish the concept of inertia and the importance of experimentation in physics. Huygens' work on centrifugal force and his understanding of the pendulum contributed to Newton's understanding of dynamics. Newton synthesized these diverse influences into a coherent and unified system, providing a more comprehensive and fundamental explanation of the physical world. It is worth recalling that Newton famously said, "If I have seen further, it is by standing on the shoulders of giants." The treatise, in turn, exerted a profound influence on subsequent generations of scientists and philosophers. Its clear and accessible presentation of Newtonian physics helped to popularize the scientific revolution and to promote a mechanistic worldview. Philosophers such as Voltaire and Locke championed Newton's ideas, seeing them as a triumph of reason and a challenge to traditional authority. Scientists such as Laplace and Lagrange built upon Newton's work, extending its scope and power. The treatise became a standard text in universities and academies, shaping the education of generations of scientists. It is difficult to overstate the lasting impact of Newton's work on science, philosophy, and Western thought. In conclusion, Isaac Newton's A Treatise of the System of the World stands as a watershed moment in the history of science. It offered an accessible and compelling exposition of his revolutionary laws of motion and universal gravitation. While the Principia laid the rigorous mathematical foundation, the treatise effectively translated these complex ideas for a broader audience. This accessibility fueled the dissemination and acceptance of Newtonian physics, transforming the scientific landscape. The treatise provided immediate practical benefits, like improved astronomical predictions. It also laid the groundwork for future developments in celestial mechanics and other areas of physics. Despite challenges and revisions over time, Newtonian physics, as presented in the treatise, remains a cornerstone of our understanding of the physical world, an enduring testament to the power of human reason and observation. It served, then, as a crucial stepping stone, propelling scientific understanding into a new era, a legacy that continues to resonate today.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.